Hello from AI Sciences and welcome to Gradient Boosting Explained for Beginners Part 1. I'm your instructor Kashif Murtaza and in this video we are going to explain gradient boosting algorithm. In fact, this gradient boosting algorithm is a combination of boosting, that is a standalone technique, and a gradient descent algorithm that is again a standalone kind of algorithm. So the combination of boosting and gradient descent together give rise to gradient boosting algorithm, which is very powerful and robust to overfitting, and it has several properties. So to explain gradient boosting, let's first get an overview of boosting as well as in gradient descent, and then we will be able to define their combination in terms of gradient boosting. Boosting at a very high level or abstract level, the definition of boosting is that, let's say you have several models, let's say f1x, f2x, maybe the classifiers or regression models, maybe the several models. Then we have x, f3x, and so on. First of all, the data is given to the very first model, whether it is a regression model or a classification model. Then this model gives some information to the next model, and the next model is trained on the same set of data. This information, in most of the cases, is highlighting the importance of some of the data points as compared to the rest. Then this model, F2, gives some information to another model, and the other model is trained. So in this way, several models are trained in a sequence. And let's say if we have trained k models, then finally one final model is obtained by combining all these models in a weighted fashion. So alpha 1 is a real number, let's say alpha 2 is a real number, alpha 3 is a real number, and alpha k is a real number. So just a weighted combination of all these different models give one final model, f of x. And that is what the boosting is. So basically you have certain models, they operate on data, they do some predictions. This prediction information is propagated to the next time step, where maybe a completely different model is trained, and the information progressively moves on, and finally at the end you'll be having several models to combine together, and you combine all these models by assigning different weights to different models. Different models may be of different importance, categorized by these kind of weights. So take home for this slide is boosting is a technique of building multiple models in sequence and finally combining these multiple models together to come up with one giant model. For more details on boosting, we already have a complete video on boosting on our channel AI Sciences at YouTube. So next we explain gradient descent algorithm. So what happens in gradient descent algorithm is that, let's say you have a particular loss function that depends upon parameters of a model f w1 and w2. Let's say you have some function that has parameters w1 and w2, and that function operates on xi and maps it to some yi. Let's say these are these parameters. Let's say this is w1 and this is w2. Now a loss function basically represents the difference or deviation of the prediction of the function and what should it actually predict, sometimes called as ground truth. Now this loss function actually depends upon the choice of parameters. For if you see this curve, at different locations, depending upon w1 and w2, the height of loss function tells how bad this function is performing. So the goal really is to bring this loss down by choosing suitable values of parameters w1 and w2. And one way of doing that is to start with any choice or random choice of W1, W2 parameters, compute a loss there, and then take a step in the direction of negative gradient. So, for example, compute the partial derivative with respect to W1 and compute the partial derivative of loss with respect to W2, and that vector is known as the gradient vector of the loss function. So that's a gradient vector with two components. These are the original components, W1 and W2. And what you do is the original, wherever you start from, you take a particular step, alpha, in the direction negative to the gradient. The reason for taking the step in the negative direction is that this negative direction of the gradient is the direction in which the loss function minimizes most rapidly. So if W is your vector of parameters, if that's your negative gradient, and that's your learning rate or step size, then this is called the gradient descent step. And this gives actually W new, which means you will reach somewhere here. Then you will compute gradient at this point, take a step in the gradient direction, then you may reach here, and finally you may reach to somewhere where the loss becomes zero or the gradient becomes zero, or you reach some point that going further from there may not be possible. It also turns out that if your loss function is convex, then gradient descent indeed reaches the local global minimum. However, if the loss function is not convex, this gradient descent actually gives you a local minimum, which in most of the cases is okay. For example, most of the deep learning theory actually describes that local minimum are just as fine. Finding out local minima, although there are techniques to go better, search better minimums, but in several cases local minima is just as fine if the function is not convex. Now that we know boosting, which is training multiple models on in a sequential way, and gradient descent, which means minimizing the loss function by taking the steps in the negative gradient direction in the parameter space, let's combine these two together and see what is gradient boosting. So in gradient boosting, first of all, why gradient boosting? In boosting, there is a very powerful algorithm, well-known algorithm known as AdaBoost. It turns out that this AdaBoost is much more suitable so this AdaBoost actually is very well suited for classification tasks. It turns out that most of the boosting techniques, including AdaBoost, are not very well suited for regression tasks. So if somebody wants to incorporate regression under the umbrella of boosting, the solution is gradient boosting. In fact, this gradient boosting is solution of the limitation of AdaBoost for regression. So whenever gradient boosting, although the gradient boosting algorithm comes with classification as well, but its basic application is for regression. So let's see how the algorithm works. We are assuming that this is a regression task, which means the target values y, they are real numbers. And this xi may belong to a d-dimensional feature space. So let's say you have n training points. Let's say I start from 1 to capital N training points. Your goal is to find out some function that maps xi to yi. Obviously, this equality doesn't hold always. So the goal really is to find out a mapping that, if not exactly, is very close to the ground truth. So what you do is, first of all, you select some loss function that whatever the function will predict, let's say this is y hat, whatever the function will predict that on ith point, and whatever the true value of the ith point is, the target is, the loss represents a deviation between the predicted value and the ground truth. select some loss. For example, any loss function can work here. For example, a square loss or any differentiable loss function works here. So let me keep this the selection of loss function general. Any loss function works here. So the first step is to initialize your model with some appropriate constant. For example, let's say that the very first model, f0 of xi, that model actually gives the some constant as a prediction, and where this y bar is actually the mean of all the y values. So yi, so 1 over n. So that's the mean value. This may be a very bad prediction because for every data point xi, the model is predicting the same value. So for example, for x1, the prediction of the model is same thing. For x2, the prediction of the model is the same thing, and so on. That's a bad thing. But let's see how can we improve these predictions. Because now you have made these predictions on every data point at the first place. Now let's compute the gradient of the loss. So our loss function now is Ly, and this is ft minus 1 of xi. That's this is our prediction. If you just focus on this value, that's our prediction at xi. And sorry, this is ground truth. I should not write a hat there on top. That's the ground truth, and that's the prediction. And if we compute the gradients with respect to these predictions, ft minus 1 of xi, then let me call these numbers as gradients. And actually I take the negative of that gradient. So let me write the negative of that gradient. So the negative of this gradient, let me call that as residual or pseudo-residual. Let me call this as it. So for every data point, I will compute the loss with respect to the prediction made by the model. When t is equal to 1, the model is this. When t is greater than 1, we will see how the model will be updated. So now we have basically a data set of xi and their corresponding residuals at time t. That's another regression data set. I varies from 1 to n. That's another regression data set. Now step 2, you actually fit a model to learn these negative gradients. This RIT is the negative gradient for ith sample at tth iteration. So let's build some model. Let's say HT. Let's fit this model into the data xi that actually predicts this gradient. So this particular function can be any regression model. It may be a regression tree. It may be a random forest regressor. It may be a support vector regressor, or it may be a deep neural network for regression task. So step 1, compute the gradients. For each data point, you will be having a real value, the gradient, negative gradient. Then fit a function to model these gradient values. So this value indeed is the gradient. Now you have gradient value available. That's the gradient value available. And you have your initial prediction available, which is ft minus 1 at xi. And then this gradient is actually the negative gradient. This gradient is indeed the negative gradient. Now you just take a step, alpha step, in the direction of negative gradient, and that precisely is what gradient descent update is. And that gives you the next model. Now this model will go back to here in the next iteration. You compute the gradient, you fit another model, maybe a completely different model the gradients. Once you have negative gradients, your original model, do a gradient step update, build a new model, and move on. Now, here is one other thing, how to compute the best learning rate alpha. There is a proper way of computing the best learning rate alpha. For example, alpha is argmin, the value that minimizes this particular thing. I varies from 1 to n, loss of yi, which is the ground truth, and whatever the function t minus 1 xi plus alpha h of txi is giving. So see, for example, this is our previous model, that's our negative gradient. So this is the prediction after taking a step in the negative gradient. But this alpha value needs to be specified. So we are specifying this value that minimizes the overall or the cumulative loss. So that's all the gradient boosting algorithm. You can see very easily the gradient descent step. That is much more visual here. But where is the boosting step? How we are actually combining the different models together. So let me write this as t here and this as t here, and let me explain the boosting step. So for example, if you just unroll this ftxi, if you just unroll this f of t xi, that is actually f of t minus 1 at xi plus alpha t h of t at xi. Now if you unroll this back, you will get f of t minus 2 at xi plus alpha t minus 1 h of t minus 1 at xi. Now if you see, if you just cross this and see this sequence, this model, then that model, then that model are being combined. And if you unroll this further, this will actually look like the following: f0 plus alpha 1 h1 plus alpha 2 h2 and so on. And this is precisely the sequential learning of different kind of models, and that's where the boosting comes from. So that's the general and very abstract view of gradient boosting. Let me show you a code for gradient boosting in Python. So we will be using scikit-learn ensemble gradient boosting regression model as GB. We will be working on Boston data set, and we'll be using train and test split and mean squared error here. So let's do it. Let's load now the Boston data set, X and Y. If you just want to see the dimensions of this data set, you can write x.shape, that is this, and you can also write, for example, y.shape, and these are 506 different points with 13 features. So now I do the split into training and validation sets using train test split with the 1% validation set. So that's it. Now I define my gradient boosting regression model, I fit the model, and finally I compute the mean squared error between the ground truth and the values offered by gradient descent algorithm, gradient boosting algorithm, and that in this particular case is 7.3104. So that's it for the basic information about gradient boosting. In the next video in this series, we will be discussing basically a hands-on example and a kind of more detailed kind of treatment of this gradient boosting algorithm when the loss function is squared loss. We will also be discussing basically the stochastic gradient boosting algorithm that actually is more robust to noise and has a better generalization ability. And in the same next video, we'll be discussing the concept of overfitting under the umbrella of gradient boosting, how gradient boosting avoids overfitting. So we will discuss the one concrete example of gradient boosting algorithm using squared laws. We will be discussing stochastic gradient boosting algorithm, and we will be discussing the concept of overfitting linked to gradient boosting algorithm in our next video. So I hope you have liked this video. Please press the like button, subscribe our channel, and share this video with your friends. Hope to see you next time.